Here is a schematic of a PSA scheme for ethene separations using an adsorbent that selectively binds ethene. There are essentially 5 different steps. We have the pressurization step. Then we have the adsorption cycle, operated typically at higher pressures, in which the feed mixture containing ethene and ethane is fed to the column, and purified ethane is recovered from the top. The adsorption cycle is followed by a co-current high pressure purge, in which ethane, which is absorbed within the pores, is purged using a portion of the product ethene. The high pressure purge step is followed by co-current blowdown, in which any remnants of ethane within the pores is flushed out of the system. And the final step is a countercurrent vacuum blowdown that is used to produce ethene of the required purity. Any ethane left within the void spaces serves to lower the purity of the product, and therefore a desirable feature of the adsorbent is that the uptake of ethane should be practically nothing, and this is the reason why an adsorbent such as UTSA-280, which practically rejects the entire ethane in the feed mixture into the gas phase, is to be preferred to an adsorbent such as MOF-74, wherein the uptakes of both components is significantly large. There is currently a great deal of research focused on the development of MOFs that are selective to the saturated alkane. The advantages of C2H4 selective MOFs is that ethylene of polymer grade purity, typically 99.95% plus, can be recovered in the adsorption cycle. The C2H6 selectivity derives mainly from the higher polarizability of C2H6 due to the 2 extra hydrogen atoms. The interactions of these 2 extra hydrogen atoms with the MOFs can be of the type such as non-specific van der Waals interactions, as exemplified by this MOF nickel BDC TED half, or the interactions of the H atoms with nitrogen atoms, oxygen atoms, and fluorine atoms, exemplified by iron peroxo DOBDC, JNU2, zinc 80Z OBA. The interactions of hydrogen atoms with the pi electrons of aromatic and heterocyclic rings as exemplified by MOF 8, MOF 15, copper QC2, and in some MOFs we have multiple synergistic interactions of the hydrogen atoms of C2H6 with the atoms and ligands of the MOFs such as CPM 733. In this context, I invite you to also watch the presentation titled Comparing C2H6 Selective MOFs on my YouTube channel. As an example of a MOF that is selective to the saturated ethane, let us consider iron MOF 74 or Fe2DOBDC that contains open metal sites of iron. These open metal sites may be oxidized to form iron peroxosites shown by these red triangles here. The two H atoms of C2H6 may bind with these peroxosites in the manner indicated in this diagram. This important development was published in Science in 2018. To demonstrate the efficacy of iron peroxo MOF, breakthrough experiments were conducted and published in the Science paper in 2018. While this development has acted as a catalyst to further MOF developments using C2H6 selective MOFs, it must be remarked that iron peroxo MOF is highly sensitive to moisture and most likely not suitable for use in commercial practice. I now address the question of screening and ranking of C2H6 selective MOFs for separating equimolar mixtures of ethene and ethane. In this graph, I show experimental breakthrough data for 7 different MOFs. It is not possible on the basis of these experimental breakthrough data to directly compare the efficacy and ranking of these 7 different MOFs because the masses of adsorbents used are different. For example, here the experimental data for JNU6CH3 uses 0.85 grams of MOF and the flow rate is 2 milliliters per minute. For JNU2, 2.4 grams of MOF are used and the flow rate used in these experiments is 1 milliliters per minute. The efficacy of MOF 15 is demonstrated in experiments that are conducted in 50-50 mixtures but also containing helium at a total flow rate of 8 milliliters per minute. The mass of adsorbent is 1 gram. For copper QC2, the flow rate is 2 milliliters per minute with a mass of adsorbent 1.037. With copper BDC, 1.2 grams are used at a flow rate of 5 milliliters per minute. With TYUT12, 1.5 grams of adsorbent is used at a flow rate of 2 milliliters per minute. And for UIO67 NH2 twice, the flow rate is 1.25 milliliters per minute and the mass of adsorbent is 0.6509 grams. It would have been much better if the published data had used a modified time parameter that factors in the influence of both the volumetric flow rate at the inlet and mass of adsorbent. So I would request researchers in the future to present their breakthrough experiments using this modified time parameter, which is Q naught, the flow rate at the inlet in milliliters per minute, times the actual time in minutes, divided by the mass of adsorbent, and the units of this is milliliters per gram. I explain this further in my YouTube presentation, Breakthrough Experiments for Screening and Scale-Up, on my YouTube channel. Depending on the pore size and topology, the breakthrough experiments may be strongly influenced by intracrystalline diffusion of the gas molecules. I show here an example of the breakthrough for copper QC2, where the experimental data results in a productivity of purified C2H4 of 0.4 moles per kilogram if, in the hypothetical case, the diffusional influences were absent. The productivity would have been 0.85 moles per kilogram, more than a factor 2 higher. For further explanation of the influence of diffusion on experimental breakthroughs, I refer you to my paper. Watch also the YouTube presentation, Breakthrough Experiments for Screening and Scaling Up. Let us gain an understanding of the analysis of breakthrough experiments. I show here an example of experimental breakthroughs for 50-50 mixtures in the C2H6 selective MOF JNU6CH3. The introduction of CH3 groups not only reduces the pore size from 5.4 angstrom in JNU6, that is a MOF5 analog. The pore size is reduced to 4.1 angstrom in JNU6CH3. Additionally, it renders an increased electron density on the pyrazolate nitrogen atoms of the organic linker, leading to enhanced interactions of C2H6 with the host atoms of the MOF. The breakthrough experiments demonstrate that C2H4 with a productivity of 22.06 liters per kilogram of high purity C2H4, meeting the polymer grade specification of 99.95%, can be achieved. To proceed further, I consider a simplified model of the breakthrough in which the concentration fronts traversing the column are assumed to be in the form of shock waves. The shock wave model is indicated in light blue in this diagram here. The background details of the shock wave model are described in my two papers listed here. The first question I address in the screening and ranking of ethane selective MOFs is the following. Is the adsorption selectivity the proper metric? From the shock wave model, the expression for the adsorption selectivity can be derived in terms of the breakthrough times T1 and T2 for ethane and ethene respectively, and delta T is the time interval between the breakthrough of ethane and ethene. The expression for the adsorption selectivity for a feed mixture of mole fractions Y10 for ethane and Y20 for ethene is the following. This is derived in my two papers listed here. The adsorption selectivity is 1 divided by 1 minus delta T divided by Y20, which is the mole fraction of ethene in the feedstock, times T1, which is the breakthrough time for ethane. Essentially, the adsorption selectivity relates the time interval delta T to the breakthrough time of the more strongly adsorbed ethane. If the adsorption selectivity is infinitely large, the time interval delta T is related to T1, which is the breakthrough time for ethane, and the mole fraction of ethene in the feedstock. In other words, the selectivity is just a reflection of the breakthrough time interval delta T to the breakthrough time for C2H6. This metric does not guarantee a high productivity value for purified C2H4 with increasing adsorption selectivity. What you need is a metric that reflects the productivity of purified alkene, in this case ethene, that can be recovered during this time interval. In this graph, I examine the productivity of polymer grade ethene determined from breakthrough experiments from the published literature for a variety of MOFs. JNU6CH3, we have copper QC2, we have IRMOF8, MAF49, and I plot the productivity of purified ethene as a function of the adsorption selectivity. We see here that the productivity of purified ethene does not seem to correlate with the adsorption selectivity. And for example here, the oft-cited MOF Q copper QC2 has a adsorption selectivity of 4, but a very modest C2H4 productivity. That this productivity is expressed in liters per kilogram. JNU6CH3 has the highest productivity in these MOFs, despite the fact that the adsorption selectivity is less than about 2. So we must conclude that ranking MOFs on the basis of adsorption selectivity is not appropriate. Using the shock wave model for a fixed bed adsorber, we can derive an expression for a metric that I have dubbed the separation potential, which is the productivity of purified alkene, C2H4, that can be recovered during the time interval delta t. The expression is given here. It is delta t multiplied by the molar concentration of the feed mixture at the inlet, pressure of 1 bar, and temperature of 298 Kelvin, times Q naught, which is the volumetric flow rate of the feed mixture at the inlet, divided by the mass of adsorbent. This expression can be rewritten in terms of the molar loadings of components 1 and 2 in the adsorbed phase that are determinable using the IAST. The expression for delta Q, the separation potential, is Q1, which is the molar loading of ethane in the adsorbed phase, times the mole fraction of ethene in the feed mixture divided by the mole fraction of ethane in the feed mixture, minus the molar loading of ethene in the adsorbed phase that is in equilibrium with the feed mixture. Q1 and Q2 can be determined from the ideal adsorbed solution theory. For 50-50 mixtures of ethane in JNU6 using the unary isotherm data, we can determine delta Q to be 1.06 moles per kilogram, which translates to 23.7 liters per kilogram. This value must be compared with the value from the breakthrough experimental data, which is 22.06 liters per kilogram, as demonstrated in a slide or two earlier. I would suggest that this metric, delta Q, is the appropriate metric for screening and evaluating your MOFs, because it is a convenient one that relies only on the IAST calculations of mixture adsorption equilibrium. Let's demonstrate the use of the combined selectivity capacity metric, dubbed the separation potential, in my papers that are listed here. In this graph, I plot on the y-axis the ethene productivity meeting the polymer grade specification from breakthrough experiments for a variety of MOFs, plotted as a function of the separation potential determined from the IAST. Since the separation potential is derived on the basis of a simplified shockwave model, this delta Q value represents the upper bound or upper limit for the achievable productivity in an actual breakthrough experiment. Indeed, we see there is roughly a linear relation between the experimental productivity with the separation potential. There are some deviations for MOF15 and UiO67NH2 twice, because the MOF15 breakthrough experiments were not actually for 50-50 mixtures, but for mixtures containing an inert gas, and the experiments were conducted at 293 Kelvin. So the actual productivity values should be towards the left and towards the bottom. The experimental data for UiO67NH2 twice is not at 298 Kelvin, but at 296 Kelvin. So this is a slight overestimation of the productivity. So these 2 points understandably deviate from the overall trend that the experimental productivity should be roughly linearly related to the separation potential. This implies that the separation potential is a appropriate metric for screening MOFs for C2H6, C2H4 separations. Watch also my presentation, Metrics for Evaluations of MOFs in Mixture Separations, on my YouTube channel. It is becoming increasingly common to compare MOFs for a variety of separation tasks using the separation potential. I show here a graph taken from this paper, shown here, wherein a variety of MOFs for C2H6, C2H4 separations are compared on the basis of the separation potential and the selectivity plotted on the x-axis. If we compare the experimental data that is also presented in this paper for the productivity of purified ethene, we will conclude that these productivities are linearly related to the values of the separation potential, as I had demonstrated in the foregoing slide. So I have two important messages to convey on screening and ranking of MOFs for C2H6, C2H4 separations. Please, when you present experimental data, use the modified time parameter, where you take the actual time multiplied by the volumetric flow rate at the inlet and divide by the mass of adsorbent. This allows an easier comparison of breakthrough experiments for different MOFs. Secondly, for initial screening and evaluation of MOFs, it is preferable to use the separation potential that is based on the shockwave model for fixed bed adsorbers. The selectivity is not an appropriate metric. A high selectivity of C2H6 to C2H4 does not guarantee a high productivity of purified ethene.